Looking at another example of finding relative extrema where there is a local max or a local minimum value and the x values those occur at. So we're given f of x is equal to 3x times e to the x power plus 2. So I notice we always need to take the derivative and we want to find our critical numbers. I notice when we take the derivative, though, notice what we have to use the product rule. We have 3x, we can treat as one function, and we can treat e to the x as the other function. So when we take the derivative of that piece, we have to use the product rule. So product rule says, let's take the derivative of the first. So derivative of 3x is just 3 times the second. So the second is just e to the x plus the first, which is 3x, times the derivative of the second. Well, remember the derivative of e, that was just itself. E to the x was just e to the x. If this was a power other than the x, we can think of it this way, either two, take the derivative of the exponent, which is 1. So really multiplying by the derivative of the exponent doesn't change it, right? Plus the derivative of 2. Well, the derivative of 2 is 0, so we don't have to worry about that. And we want to know, when is f prime of x equal to 0? And we want to know, when is this derivative undefined? Well, your e function, that's defined everywhere. We don't have to worry about any trouble spots. And there's no variable in the denominator. We don't have any natural logs. We don't have any square roots. We are good. So this is defined everywhere. So we only have to worry about, when is this function 3e to the x plus 3x e to the x equal to 0? So start out by factoring. Notice they both have a 3 in common in both of those groupings, and they both have an e to the x in common. So we can actually pull out a 3 e to the x. If you pull that out of the first grouping, notice there's nothing left except a 1. Plus, if I pull out 3e to the x from the second grouping, the only thing I'm left with is a single x equals 0. So we're looking at when each piece is 0. So 3e to the x equals 0. And when does 1 plus x equal to 0? Well, it's helpful to know what your function e to the x looks like. That is never going to equal 0. This is a function that looks like this. And it gets closer and closer to that x-axis as x goes to negative infinity, but it never touches, never crosses. So this 3 times e to the x, this never equals 0. So we're only worried about, when is 1 plus x equal to 0? Well, if we subtract 1 on both sides, we get that's when x is negative 1. So there's only one critical number. So we want to see what's going on the left-hand side of negative 1 and on the right-hand side of negative 1. And we're going to plug that into our derivative. And I'm going to look at my derivative. I like it better in factored form a lot of times. It's just, again, easier to see if it's positive or negative. So if I choose a number which is less than negative 1, so how about x equals negative 2, and we plug that back into our derivative, well, 3e raised to the negative 2 all times 1 plus negative 2. Well, notice my graph again. Any value I plug in, x is negative. It doesn't make my y value negative. These are always positive. So 3 to any power, e to any power is positive. So this is a positive number. and 1 minus 2 is negative. And so a positive times a negative, to me, then when I multiply that out, is less than 0. And so my function is decreasing on the left of -1. So choose a number bigger than -1. Well, 0 falls in there, so maybe we should choose x equals 0. So if I look at f prime of 0, this is equal to 3e to the 0 all times 1 plus 0. Well, e to the 0 is 1 times 3 is 3, so that's positive times a positive, which is positive. So that's greater than 0, which means my function is increasing on the right of -1. So looking at that, I can tell from decreasing, then going back up to increasing, that's going to give me a minimum value. So we know a min occurs at x equals -1. So we need to figure out what is that minimum value. So we want to plug that back into the original function. So that would be 3. See an x there, we're going to plug in a -1. E raised to the -1 plus 2. Well, it depends on if they're going to want us to have this as an exact answer or not, or if we want to round. So 3 times -1, this is -3. We can rewrite e to the -1 power. We can make that positive, right? By using rules of exponents, we can bring this e to the -1 down to the denominator to make that exponent positive. So all over e plus 2. So just see how your homework would want it. If it said exact answer, we could leave it like that. My guess is they might want you to round, and they would tell you usually what to round to. If I round it, so -3 divided by e. So when you put e in your calculator, it might give you a caret. Just put a 1 there because this is e to the first power. We get approximately 0.896. So I put a squiggly equal sign. That means that I've rounded in here. So I've approximated that. So this is our min value. So our minimum value is the 0.896, and it occurs when x is -1. We're looking at another example where we're finding the relative extrema and what values of x it occurs at. We're given that f of x is equal to x squared, all divided by the natural log of x. So there's a couple of things we need to worry about in this function. First of all, we can't have values of x, which gives us a 0 in the denominator. So it's undefined. When the natural log of x is equal to 0. So we could solve for this if we wanted, right? If we rewrote this in exponential form, natural log is log base e. So this is e to the 0 is equal to x. So that's just the rules definition of a log function. Take our base, raise it to the other side is equal to x. So e to the 0, that's just 1. So x equals 1. Okay, so we know x cannot equal 1. It's not in our domain. The other problem, though, is natural log of x. When you take the natural log of a value, that value has to be positive. So this is also undefined. Natural log of x is undefined when x is less than 0. Actually, less than or equal to 0. So for our domain of our original function, and this is just going to help us when we go back in to plug in points. We don't want to plug in points that don't fall in our domain. So the domain of this original function is, we're looking at all values from x equals 0, not including, to 1, not including, union 1 to infinity. Okay, so we want to find our critical numbers, and we're going to find the derivative to do that. Looking at the derivative, I notice I got to apply different rules. I need to use the quotient rule. Quotient rule says we're going to look at the derivative of our numerator. So derivative of x squared, which is 2x, times my denominator, natural log of x, minus my numerator, which is x squared, times the derivative of the denominator. So recall derivative of natural log of x. That was 1 over what you were taking the natural log of, which was x, times the derivative of x, which is 1. All over the natural log of x. And this is quantity squared. So let's clean this up a little bit. Notice that that second grouping in the numerator, we have x squared times 1 over x. So we can simplify that. So f prime of x is equal to 2x natural log of x minus x all over the natural log of x, which is quantity squared. Okay, so looking at this, notice you can factor out an x in the numerator, and that will help us when we're solving for that equal to 0. So derivative f prime of x is equal to pulling an x out of the numerator. That would leave us with a 2 natural log of x for the first grouping, minus 1. All over the natural log of x, quantity squared. Okay, so again, critical numbers, where that is set equal to 0, really we only look at when the numerator is 0. And where this is undefined. And we looked at natural log of x was undefined when x was 0. I'm sorry, x was 1. I'm not going to worry about the negative numbers. I just need to know when I'm checking my points, I'm not going to look at negatives. Okay, so now setting this derivative equal to 0, if I multiply both sides by my denominator, that goes away. And so I'm just left with x times 2 natural log of x minus 1 is equal to 0. So now I'm setting each piece equal to 0. So I'm looking at when is x equal to 0. That's pretty self-explanatory, right? 2 natural log of x minus 1 equal to 0. Okay, so I'm going to solve for this. We're solving log equations. Let's isolate your log on one side of the equation. So we're going to first add 1 to both sides. So we have 2 natural log of x is equal to 1. We want to isolate the natural log, so let's divide both sides by 2. So this gives me the natural log of x is equal to 1/2. Now use your definition of logs to rewrite it in exponential form. So take our base, raise it to the other side is equal to what you're taking the natural log of. Well, our base for the natural log is e. So e raised to the 1/2 power equals x. Another way to say that, right, is x equals, I can rewrite 1/2 power as a square root, so square root of e. Okay, so these are our critical numbers. So this is a critical number, critical number, critical number. If I put this on the number line though, we had talked about that the x couldn't be negative. We actually talked about the x couldn't be 0 too, even though that's a critical number. It's undefined at 1. Let's put 1 in there. Square root of e, that's a square root of 2.7, so that's bigger than 1. Let me just give you an approximate. That's approximately, square root of e is approximately 1.65. Okay, so there's a couple intervals we have to choose, something between 0 and 1. How about x equals 1/2? And we're plugging this back into the derivative. So we would have 1/2 all times 2 natural log of 1/2 minus 1 all over natural log of 1/2 quantity squared. Let me just see what the natural log of 1/2 is. I believe it's negative. It is negative. It's a negative 0.7. So let's just kind of think about this. 2 times negative 0.7 is negative 1.4 minus this 1 here. So if I plug in 1/2, my numerator inside that parentheses is negative. So I notice I'm going to get a negative number in my numerator. But this bottom piece, even though natural log of 1/2 is negative, I'm squaring that whole bottom piece. So squaring any number is positive. So I notice that that derivative is less than 0. So it has to be decreasing between 0 and 1. So let's choose something that's between 1 and e. So how about x equals 1.5? So if I'm looking at the derivative and I'm plugging in 1.5 wherever I see an x. Okay, so going in, plugging in 1.5. So I have 1.5 times that quantity, 2 natural log of 1.5, and then subtracting 1. So let's look at natural log of 1.5. I know that's positive, but let's see how big it is. That's 0.4. So if I multiply this 0.4 here times 2, that's 0.8 minus my 1. That would make that inside the parentheses negative. So my numerator looks like it's negative all over my denominator, which is positive. So it's less than 0. So this is also decreasing here. So that critical number, x equals 1, which it was undefined at, there's an asymptote there. It's not a max or a min. So we have one more interval that we have to look at, and that's something that's greater than square root of e. Square root of e was 1.65, so maybe let's look at x equals 2. So if we go in, plug this into our derivative, 2. That would be 2, all times 2, natural log of 2 minus 1, all over the natural log of 2 quantity squared. So natural log of 2, that's 0.69 or 0.7 times this 2 right here in front. That's going to give me 1.4 minus 1. That's positive number in my numerator. All over a positive in my denominator, which is a positive number. So this is greater than 0. So greater than square root of e, we're going to be increasing. Here at square root of e, this is changing directions. It is defined at square root of e. So if we're going from a minimum, and then so decreasing and then starting to increase, we know that that value right there is going to be a min. So a min occurs at x equals square root of e. So we want to find out what is that value if I plug that square root of e back into my original function, which is way back up here. Let me just pull that down. So f of x is equal to x squared all over natural log of x. So looking at this, we have f square root of e. So we get e, the square root of e squared, all over the natural log of the square root of e. If we want to, let's rewrite that as e to the 1/2 on the bottom. Well, if I square root, that's going to fall away. So that just gives me an e in the numerator. The denominator, so this is saying, what am I going to raise e to get back e to the 1/2? Well, I have to raise e to the 1/2 power to get back e to the 1/2. So we can invert multiply by the denominator because we're division fraction. So this is really just 2e. So our minimum value is 2e. And it occurs, oops, when x is square root of e. So here's the case. If I was asking me to put down where it was increasing and decreasing, here's the case where I would not put in 1 because this was where it was undefined. So if it asked me where is it decreasing in this case, it's starting, not including, because that's not my domain, 0, going till I get to 1, but not including because it's not defined there, union, not including 1 to the square root of e, not including. And if it asks me where it's increasing, that would just be the square root of infinity to infinity. Square root of e to infinity. Hopefully you guys can see that. It gets really small when I take up too much space. Okay, so we just finished 5.2.